We're going to look at a second method of converting from hexadecimal to denary, which is just the standard number system that we use. So suppose that we've got something like 48. You might have a little 16 next to it just to say that this is in base 16 or hexadecimal, but don't worry about that. And you ask to convert it into normal denary, standard numbers, then it's a really simple technique. You just take the first digit, which is 4, and you times it by 16. So you do the same thing each time. You just take the first digit, times it by 16, and then you add the second digit, the 8 in this case. You have to show all your working when you do these, so do each little step. That's 64 plus 8, which is equal to 72. And that's it. Just times the first digit by 16 and add the second digit. Let's have a look at another one. Suppose we've got a letter this time. Suppose we've got a 3. Take the first digit, which is A, but A actually stands for 10, and it is useful just to, jot these down. So you've got A, B, C, D, E, and F, and just get that that's 10, 11, 12, 13, 14, 15. Don't take any chances. It's just so quick and easy just to jot those down. So that's 10 times 16 plus 3, which of course is equal to 163. Okay, let's do one with a couple of letters in maybe this time. Let's have CF and see what we've got there. So we've got 2 digits then. So we've got the C, which is 12 times 16, and then we have to add on the 15, and then we'd work that out. So we've got 12 times 16 plus 15, which is equal to 207. Okay, doke. Let's just look at one more. You don't have to know why this works, but it's nothing particularly amazing. So suppose you had something like 50, say, or 50 in hexadecimal. Just put that 16 just to say this is in hexadecimal. You could think about that in binary fairly easily. That's just 0, 1, 0, 1, and then 0, 0, 0, 0. Just to sort of remind ourselves what's happening there is that you've got the 5 in hexadecimal is just this nibble, and the 0 is this nibble. But what you can see here actually is that this is 5, but then you've got 4 zeros next to it, and what that means in binary is that you've times by 16 with those 4 zeros that side. It's been shifted. The number has shifted over to the left. It's a left shift of 4. So you can kind of see why that first digit has to be times by 16. It's no different from, if we just got normal math. Suppose we've got something like 70. This really is just equal to 7 times 10 plus 0. Or if we had something like 73, that really is just 7 times 10 plus 3. But because we're in base 16, we're not timesing by 10, we're times by 16 instead.